organizing committee for systematically coordinating and making this event a reality within such a short period of time. Special thanks goes to Professor J.R. Kyle and Dr. Saurabh Barua for their kind support. And can we have a huge round of applause, maybe e-claps, for all the participants representing 30 countries from diverse fields of studies within and beyond the domain of seismology and tectonics. Now may I request our director, Professor G. Nohar Sastry, to deliver his welcome speech, please. Over to G. Nohar Sastry, sir.
Now can you go on live? Namaskar and good morning to all of you. On behalf of CSIR East, I welcome all of you for this international virtual workshop on global seismology and tectonics, which is going to present a number of eminent speakers who are internationally well known. And I thank Professor Andrew McHale from United States Geological Survey, US, and our mentor, Professor J.R. Kayal, the Deputy Director of Geophysics Department of GSI, Dr. Baru, the senior most scientists of the institute working in this geoscience area, and the convener of the workshop has taken a lot of care and paid attention to the details. Dr. Shantanu Barua, senior scientist, CSIR East, and the convener, and other colleagues, Dr. Manoj Kumar Pukan, Dr. Vijit Kumar Chaudhary, Dr. Devashish Mohanty, Dr. Chinmay Rajkonwar, and all other members of Geoscience family and the NEAST family for this occasion, and distinguished scientists, academicians, researchers, and students, especially around the globe, formed a great basis for us to come together and participate in this international virtual workshop on global seismology and tectonics. I am very pleased to note that there are participants from over 30 different countries, ranging from Albania, Algeria, Argentina, Australia, Bangladesh, Canada, Colombia, Comalcalco, Tobago, Democratic Republic of Congo, Dominican Republic, Ecuador, Iceland, Indonesia, Iran, Israel, Malaysia, Mexico, Myanmar, Nepal, Nigeria, Philippines, Poland, Russia, Singapore, Sri Lanka, Taiwan, Tajikistan, Turkey, and US, apart from India, which is the organizer. And we're very pleased to know that over 1,000 people have registered for this workshop. Sometimes when there are challenging situations like COVID-19, it also creates opportunities to do things differently and also to do different things. So we are able to have this particular workshop as a virtual workshop, and we can have a relaxed 12-day workshop where probably some of the most eminent people who are internationally recognized in the field of seismology and tectonics are going to share their thoughts. And more importantly, these lectures are available on YouTube, even for people who miss their lectures. And this will be a fantastic platform for all of you to come in contact with the best of the best minds around the world. And I sincerely appreciate efforts of Dr. Shantanu Barua and his entire team for taking this very, very important task of conducting this virtual workshop. I feel that geoscience, tectonics play a much bigger role than most laymen could think about. Geoscience or earth sciences as a domain of study is rapidly evolving. Currently, this is probably evolving and expanding at a much bigger pace due to the advent of computational approaches. And the advanced computational approaches have given a lot of strength to many of the activities that one takes in this seismology and tectonics. And these methods has a profound importance in the way in which the human race is evolving. Physics, chemistry, biology underwent revolutions at the beginning of 20th century. Probably the revolutions have come in physics first, followed by chemistry and biology, whereas earth science entered such a revolution in late 60s. The theories of seafloor spreading and plate tectonics for the first time offered unique explanations for that before had seemed unrelated observations. Now they are able to connect these seemingly unrelated observations in the fields of geology and geophysics. However, especially in the last 2-3 decades, a trend towards integration of computational methods, especially in the geophysics front, conspicuously emerged in developing numerous models towards understanding the subsurface dynamics. This plays a very important role to look at different types of dynamics that are there in the subsurface. And in the present scenario, computational techniques have shifted to the application of different methods like machine learning, deep learning, and artificial intelligence. I'm not an expert in earth science, but I quite appreciate how this particular field is evolving, and we are all very much looking forward to listen to the most eminent speakers in this particular area. And the eminent keynote speakers of the workshops are pioneers and stalwarts in their own subject areas. And the lecture sessions aim to imparting information, the contemporary information on the impending topics and estimating earthquake completeness, large intraplate earthquakes in especially India and related areas which expands that earthquake, ground motion and damages, tectonics and seismicity of Indonesia and Southeast Asia. The deformational processes in the Himalayan megathrust, earthquake precursor for our forecasting, seismic hazard and seismic source modeling, tectonics of Northeast India in particular are some of the most important focus areas that our institute is aimed at, and I am extremely happy that our institute is conducting this very important workshop, and this leads to opportunities to brainstorm about the issues of contemporary interest. And as this is spread for almost over a fortnight, it will give a good platform for people from different countries and people even from interdisciplinary areas within the larger domain of earth sciences and geophysics and geosciences to come together and enjoy the spirit of doing science internationally. This is very important. Science is something which will provide a knowledge for us to excel in every walk of life. And during the COVID times, some of the students are probably confused. worried or demotivated. But it's very important to understand that when a tough situation comes, we have to have much stronger willpower to combat. And this particular workshop, I'm sure, will be a great step for many young people to listen to the stalwarts in the field and get motivated. And once again, I'm very, very lucky to have such a dedicated team at CSIR NIST who have come up with innovative idea of conducting this important workshop, the International Virtual Workshop on Global Seismology and Tectonics. And I'm also very, very thankful to all the speakers who has spared their valuable time to work and to participate in this. And particularly, I'm very happy that Professor Andrew Michel and Professor J.R. Kayal are going to be leading us from the front along with many others. And I also thank Dr. Shantanu Burwa, Dr. Saurav Burwa and all geoscience people to participate and then take lead in conducting this workshop. Last but not the least, I thank all the participants from India and abroad, from different countries and from different states in our country, to take the full advantage of this particular workshop. And I hope that this workshop will be of great experience and use and a source for connecting to a number of important, eminent people across the globe for young and not so young people. Thank you very much. I wish all the success for this workshop, and I sincerely request all the participants to make full use of this particular workshop and then ask questions, participate and improve your knowledge, and more importantly, get motivated to do the best possible work. Thank you. Thank you very much, and I thank the organizers for giving me this opportunity to speak on this occasion. Thank you.
Thank you very much for your kind words, sir. Now may I request Professor J.R. Kyle for giving his initial remarks to this international workshop. Over to Kyle, sir.
Thank you, Shantanu, for this opportunity. I think we are all overwhelmed by the motivating and welcoming address by the director, Professor P.M. Shastri. I think it is because of him such a great event could be arranged by the NEIST Geoscience Division, and Shantanu Borua, the convener of this workshop, took a lead, but all members, every member has tremendously worked for this event. It's an remarkable, I think, milestone event for the Geoscience Division in NEIST in Jorhat. We are really feeling so excited, so encouraged. Particularly the director NIST, the way he has addressed this workshop, we are really overwhelmed, and we will try our best to see that it's a great success. Now, in earth science, seismology is a bit younger science. It's not even, 150 years old or so. In India, the first observatory was established after the 1897 great earthquake in Ceylon in northeast India. That time India had no seismic station, that earthquake was recorded instrumentally by the stations outside India. Then the first station was established in India in 1899 in Alipur, Calcutta. Then gradually the seismic stations were increased in the national network, and it was under the auspices of India Meteorological Department. But still before 1960s, the network all over the world and in India, it was in particular was so meager that we are not doing really justice to this science. Then since 1964, with the inception of the worldwide seismograph, WWSSN, the things bit improved. USGS was the leader for that network. In India also they established some 5 stations, including Shillong Observatory. But with the advancement, particularly with the digital system, the global network has now improved much by the GSS network, and India also has equally equipped its network. And NEIST Jorhat is possibly one of the pioneer institute where the digital telemetric network was established in early 2000. And with this digital system of records, now the science is getting much rich and richer every day. The seismologists in 1950s or before that used to locate the earthquakes manually by compass on the on the map. Today, they are imaging the 3D structure of the interior of the Earth with the very precise records of digital system. And I remember our collaboration with international institutes with the digital data of NEIST, and we have done quite a bit of work for the Northeast India, but much remains to be done. However, the NEIST has taken this lead. This is, I think, first of its kind to have this virtual international workshop where so many countries, so many participants are connected. This is a remarkable, overwhelming event, I feel, and hope this workshop will be a great success. And we are starting this workshop with a lecture of Professor Michael of USGS, and I think this start will take us to a great peak of success by within this fortnight of this event. So my hearty welcome to all who are connected to this workshop. My hearty thanks to the organizers, to each and every one, and to all the speakers. So let us hope that we do the justice of this great event. Thank you all.
Thank you very much, sir, for your kind words. Now, may I request Dr. Saurabh Barua to give his initial remarks. Over to Saurabh Barua, sir.
Thank you, Shantanu. Professor Andrew Michael from USGS, Professor J.R. Kayal.
Sir, excuse me, sir, your video is not coming, sir.
Yeah, is it the, it's, yeah. Professor Andrew Michael, Professor J.R. Kayal, Director CSIR NIST, Dr. G. Narahari Sastry, the convener of this international virtual workshop, Dr. Santanu Borua and his team, and all the participants. A very good morning from India and very good evening from India as well. This virtual workshop, 30 representative from 30 countries throughout the globe, and indeed, I congratulate and Teros convener and has done a splendid job to carry forward this particular workshop. Why this workshop has been designed and curated in this part of the very reason is the Northeastern produced of 12 1897 and 15th August 1950. Apart from these two great earthquakes, there are 20 large earthquakes, which is above 7.0 magnitude. The earthquake particular reason is experiences daily number of earthquakes, and almost in a 6 monthly basis there is a 5 magnitude earthquake in this particular region. So we wish to build an earthquake resilient society where seismic hazard assessment is the prime theme of GSCD besides seismic vulnerability assessment. But to initiate with these two goals, to this objective, the most important domain is the basic scientific research. And what has been coined here with different researchers, eminent researchers of the globe to talk and discuss about the basic researches, exchange our views so that we can look forward to a earthquake resilient society. That is the ultimate goal of this very new branch of science, that is seismology. Professor Kayal has elaborated the almost domain of this virtual meeting. I'll not elaborate much. We are very eagerly waiting to hear from Professor Andrew Michael. So with this brief remark, I look forward to a fruitful discussions, fruitful questions in this during period of virtual seismology, earthquake seismology virtual workshop. So this is what I wish to convey, and above all, I request all the participants to be very interactive during these sessions so that we feel that you are across the globe, you are with us, you are on this virtual meeting. With all the best wishes, I over the domain platform to Dr. Santanu Borua. Thank you. Thank you so much. Santanu, you are not audible. Santanu, you are not audible.
Now let's get familiar with the keynote speaker for the day, Dr. Andrew Michael. He has been a geophysicist with the US Geological Survey Earthquake Science Center. Center in Menlo Park since 1986, where he combines observations of earthquake processes and statistical models to determine long-term and short-term earthquake probabilities, to evaluate proposed earthquake prediction methods, and to better understand how stress and structure function as part of seismogenic process. Dr. Michael did his graduation in 1981 from prestigious MIT and master's in 1983 from another prestigious institute, Stanford University. From the same university, he pursued and completed his PhD in the year 1986. He authored more than 100 papers and reports, including publication in renowned journals like Science, Nature Geoscience, Journal of Geophysical Research, etc. He was the editor-in-chief of the Bulletin of Seismological Society of America from 2004 to 2010 and served on the Society's board of directors from 2014 to 2019 and was its president from 2017 to 2018. In 2011, for that work, he received the Society's Distinguished Service Award. Let me wrap up here and request Dr. Andrew Michael to take over the digital space and enlighten us all with your lecture on why it is hard to count earthquakes, estimating earthquake completeness. The participant may put their questions via the question and answer button, which will be attended as per speaker's convenience during the question and answer session. Over to Professor Andrew Michael, sir.
Thank you, Dr. Brewer. It's really wonderful to see everyone, to see you tonight or this morning or every time around the world. I am very, very impressed by what has been put together by you and your colleagues at NEIST. To have 1,000 people register for a meeting at this time and to share ideas it's just, I'm really grateful, and I'm grateful to have the opportunity to speak. And so with that, I will start my PowerPoint and share my screen. Hopefully this will all work. Okay, can you assure me that you see my screen and you see the opening slide? Yes. Good, okay. Okay, so the title is about a very simple topic, but it's really quite deep, which is why it is hard to count earthquakes. And, you know, the background of this slide is a map of the world with earthquakes and also volcanoes on it. And, you know, there's so much we can learn here. As one of the, one of the first speakers mentioned the mid-ocean ridges, and we can see the mid-ocean ridges in the seismicity of the Earth. And we can see subduction zones. I mean, just looking at a map of the earthquakes and volcanoes of the Earth can teach us so much. But what gets really important is answering questions about it, and as was also mentioned, the ability to estimate hazards, to assess hazards around the world so that people can prepare for earthquakes. So that will really be the final topic of the talk that we will get to as I set up this question. So one thing that's true now is it's very easy to obtain earthquake catalogs. You can go on the internet and you can go to the USGS Comprehensive Earthquake Catalog, which we just call COMCAT. You can go to the International Seismological Center and many, many other networks. And to me, this is a revolution in doing research. When I first started in the field, a colleague would send first a letter and then email and say, could you send us some earthquake data? And we would have to put it on a magnetic tape and mail it to them. And now in a matter of minutes, you can receive data, but this also means that people sometimes get data and they are not careful with it because they don't realize all of the problems that it might have because they're not in contact with the people who created the data. So here is the COMCAT search page, and I just did a search, I did this last night, for earthquakes in the last 5 weeks. So if I then show you the result, this goes down to magnitude 2.5. All of a sudden, I see earthquakes all over the world, and once again, we can see features like the mid-ocean ridge here in the Atlantic Ocean. We can see, lots of earthquakes around the Ring of Fire, the subduction zone, and including in India and Northeast India. And I'm going to zoom in right now, just because it's been very active lately, on the subduction zone in Chile. And I love earthquake catalogs because you can learn so much about the Earth. So if I go into this area, here's the coastline of South America and Chile. The red line is the trench of the subduction zone. And I can go in and I can query each of these earthquakes. And I discover that the ones near the trench are fairly shallow, only 16 to 23 kilometers. And as I go further into South America, they get deeper, 135, 279, and even 575 kilometers deep. And of course, what we're seeing here is the downward going Pacific plate going underneath South America being outlined by these earthquakes. So there's just so much power that we can learn from earthquake catalogs, and we can get them so easily. So we can also, from the USGS site, if you scroll down the list of earthquakes on the left-hand side, if you do a search, there's a download button. And you can get the download in the data in a number of formats, comma separated or GeoJSON, and KMLs are good with Google Earth. QuakeML is good with OBSPy for very advanced users. It has lots and lots of information about each earthquake, more than I usually need. So just to show you what this looks like, this is an earthquake catalog. So it's a lot of numbers. And this catalog here is in the comma separated values format. It's fairly easy to read. I could even go in and say 2020, there was an earthquake on September 13th at 4:42 UTC, and I have the latitude and the longitude and the magnitude, and all this information is there. And a program like Excel can read this very easily. You can get it in a different format that looks equally messy. But this format is GeoJSON, and it's very easy to read into programs such as R. I'm a big fan of the statistical package R. Not only do I find it very useful, but the fact that it is open source and completely free and works on every type of computer I think is very important. But many of my colleagues will do this in MATLAB, and which I only have the problem with that it costs a fairly large amount of money and so isn't always available to everybody. So that's what an earthquake catalog looks like. But we really have to look at it in detail to understand what we can do with it. So the first question I want to point out is the question, are earthquake catalogs data? And I'm going to say the answer to this question is no, they are not data. And this is a fairly old figure, but I think it makes the point. Data are seismograms. So each one of these is a seismogram. Here for station A, this is San Francisco here. Maybe some of you have been there for the American Geophysical Union meeting. I actually live right about here on the coast. And you have a seismogram, and 16.5 seconds after the minute, the P wave arrives. Here at station C, it happens 11.3 seconds after the minute. And that's the first station where the P wave arrives. So we know that the earthquake, if we locate it, will be somewhere fairly close to station C, closer to station C than to any of the other stations that are shown here. Seismograms are data. Seismograms are an actual observation of something the Earth did. Of course, even they aren't an exact representation of ground motion. We have to remove the instrument correction if we want to get to the true acceleration or velocity of the Earth. So I want you to remember this always. Seismograms are data. Earthquakes are the result of analysis. They're actually the results of the analysis of analysis. The first analysis is picking arrival times and amplitudes to compute magnitudes. The second analysis is the analysis to locate the earthquakes and compute the magnitudes. Okay, so we need to be careful with earthquake catalogs. So here I'm going to take, this is California here and Nevada, and I want to look in detail at some earthquakes that happened this year. And here is a map of them. This earthquake over here is a sequence that's known as the Monte Cristo Ridge earthquake. It's in the state of Nevada, and this one is the Bodie, California earthquake. It was a smaller earthquake, not as big an area. Let's look at the locations. I mean, this looks like a bit of a mess. It's a big blob in both places. So here I show the original plot here with all of the events, over 12,000 events down to magnitude 1 that were recorded this year in these areas. And now I remove most of the events. So I only look at the ones magnitude 2 and greater, and I only wind up with about 2,900 earthquakes. And particularly the Bodie sequence, we start seeing maybe a vertical fault plane here. And this one's still a bit of a blob, although a smaller blob. And so this catalog may be in this area we're complete to magnitude 2, but that is all. So this would be all the magnitude 2 and greater earthquakes. But if I want to look at fault structure, I don't really care about having a complete catalog. I want to make this point. You don't always need a complete catalog. Here I get about the same number of earthquakes, but it's a different set of earthquakes. And I'm using all the earthquakes that were located on 23 or more stations. So in particular, this Monte Cristo ridge sequence in Nevada, you start seeing that there may be a cross fault more clearly. You could see it a little bit in the plot on the right, and you get just a better image of the fault plane that goes in this direction. So in some cases, we care mostly about getting the best located earthquakes. And very simply here, I do that by selecting the ones recorded on a lot of stations. Notice that while the earthquake in Nevada looks better in the left-hand plot with a lot of stations, the Bodie earthquake looks better here with the bigger earthquakes in it. One thing to realize is with ComCat that comes from the USGS, I know it's very easy and popular to use, it is a catalog of catalogs. So the state border of California and Nevada runs in between these two clusters of earthquakes. And so the earthquakes on the right in Nevada were located by the Nevada network with slightly different methods than the ones located in California by the Northern California Seismic Network, which is run by the USGS and UC Berkeley. So always be careful that when you look even at, especially when these big global catalogs, it's pasted together from lots of catalogs that may have slightly different things. So just remember, to study the structure of an earthquake sequence, we don't care if the catalog is complete above some magnitude. What we want are the most accurate locations. But there are other problems where we will care very much that the catalog is complete, and now I will move to those. Okay, so let's start counting earthquakes. So we're going to count earthquakes from the start of 1960 to the end of 2019 for a period of 60 years. And if I count magnitude 9s and above, there are 4 of them. And I think we're fairly confident that we've recorded and we have not missed any magnitude 9 earthquakes. In fact, most of us probably know the names of all these earthquakes. We have the 1960 Chile earthquake, the 1964 Alaska earthquake, the 2004 Sumatra Andaman Islands earthquake, and the 2011 Tohoku-oki, Japan earthquake. If we go down another magnitude unit, of course, we get more earthquakes. So there's 51 magnitude 8s in the ComCat catalog for this time. We don't know all of these earthquakes, I'm sure, but notice that they tend to be largely around the subduction zones. Now, if we go down to magnitude 7, we see much more of the world filled in, and we get actually more than 10 times as many earthquakes, 837 earthquakes. And we can keep doing this. We get 8,420 magnitude 6 earthquakes, and this is what we expect, an increase of about a factor of 10. Every time we go down 1 unit of magnitude, we get about 10 times as many earthquakes. If we go down to magnitude 5 and 4, I will not draw maps because this program won't let me handle so many earthquakes on a map. But again, at magnitude 5, it's almost a factor of 10 greater. Maybe we think there really were 81,000. Maybe that's a little incomplete. It's hard to say for sure from just what I'm showing you here. But at magnitude 4, we see we only get 5 times as many earthquakes as magnitude 5, 427,000 earthquakes. So if someone says how many magnitude 4 earthquakes have happened in the last 60 years, the answer I'd have to say in the entire globe is I don't really know, because we do not have a complete catalog of these earthquakes. I could tell you probably how many 5s and almost certainly how many 6s. Okay, so when we answer these sort of questions, we start counting earthquakes, we have to pay attention to catalog completeness. All right, here's another question we were often asked. Is the rate of earthquakes increasing over time? So I'm going to look at here a catalog called ISC-GEM, and this was the version 1 of their catalog. They're up to about version 7 by now. So ISC-GEM is the International Seismological Center, And under the sponsorship of the Global Earthquake Model, they did a lot of work on reprocessing and continue to do a lot of work of reprocessing earthquakes from 1900 onwards. So this plot here, we have years across the x-axis. And then we have the number of earthquakes. It's a cumulative number plot of magnitude 6 and greater earthquakes. And if you're just make this plot and you're not careful, and this happens a lot. So anywhere that things are steep, the number of earthquakes is increasing faster than where the plot is less steep. You would say, looking at this plot, that the rate of magnitude 6 earthquakes is increasing over time. But of course, as we were told by Dr. Kayal, about 1960 and 1964, there was a big increase in the number of stations. This is the installation and finally completing it in 1964 of the Worldwide Standard Seismographic Network, WWSSN. So really before 1960-64, we don't think we knew all the magnitude 6s in the world. And so this is an artifact of the fact that our networks have been getting better with time. One thing we can always do is to make an exploratory plot. I think people should always do this to look at their data. The magnitude time plot, very useful. So here we have years again across the plot, and we have magnitude on the scale, and each earthquake is a dot. And of course, we can see that, in the early part of the 20th century, there were not very many earthquakes below magnitude 6.5 recorded. And so we shouldn't be trying to look at magnitude 6 and greater earthquakes. So let's look at magnitude 6.5 and also magnitude 7 earthquakes and see how we answer the question about increasing rates with them. So here we're 6 again. It looks like it's increasing, but we now have seen this is not a good catalog for magnitude 6. We go to 6.5. It looks like a very little increase over time, so much better answer to the question, at least from end of 1918, really the end of World War I onwards. It's almost the same, maybe a slight increase in 1960. And if we go to magnitude 7, we see more wiggles because, of course, there are many fewer earthquakes. But really, from the end of World War I onwards, despite the wiggles, it's pretty constant. And so we would say to people, no, actually, the rate of earthquakes around the world is not increasing for the data we have. That's good data. I think you also have to remember, though, to be careful about which catalog you use. So on the right-hand side here, I have the same plot for magnitude 7 and greater. And if I draw a straight line here, we see that maybe there's a deficit of earthquakes between 1940 and 1960-ish. Another deficit here. We know that the seismicity in the world sort of slowed down for big earthquakes in the early 1980s and late 70s. There weren't very many big earthquakes for a while. It was a strange time. This is a different catalog. It's an earlier catalog, the Centennial Catalog, and I originally used this before ISE-GEM existed, and you see that there seems to be instead a bulge upwards. This catalog has many different types of magnitudes in it, and in particular, it's well known to people who really understand global seismology that in the middle of the century, in the 40s and 50s, that there were some overestimates of magnitude of surface wave magnitudes around the world, and that this affected the apparent rate of earthquakes. So I only learned about this because I asked the people, Bob Engdahl, who was the lead author of the Centennial Catalog. So you have to go sometimes to people and ask them. The ISE-GEM catalog, they took all the earthquakes and tried to compute moments for them and moment magnitudes. And so it's an improved catalog. And if they didn't have a moment magnitude, they converted things like surface wave magnitude to moment magnitude. So catalogs get better with time, fortunately. But you have to look at the details and sometimes ask questions. Okay, so now the really important part of the talk. We're going to talk about counting earthquakes for probabilistic seismic hazard assessment, or PSHA. So PSHA combines the rates of earthquakes and the ground motions that would predict it to occur if an earthquake happens, and we get the probabilities of ground motions. So large earthquakes, of which create the biggest ground motions, are rare, and so it's hard in many areas to just count the number that have happened, because We don't want the number in the world, we want the number near a particular location. And so that becomes a small number. So what we often do is estimate the rate of large earthquakes by extrapolating from small earthquakes, because there are many more small earthquakes. We can do a good job of estimating the numbers of small earthquakes if we have good seismic networks. And then we can use the Gutenberg-Richter relationship to extrapolate to large earthquakes. So this is a very important relationship in seismology here in the middle of the slide. And what it says is the log of the number of earthquakes greater than some magnitude is equal to a linear relationship, A minus BM. So we always do minus BM because with increasing magnitude, there will be fewer earthquakes. So we have here the number of earthquakes with some greater than some magnitude. A and B are constants. B, interestingly enough, is generally about 1, which is why we say when we go down a unit of magnitude, we get 10 times as many earthquakes. And A is the log of the number of earthquakes with magnitude greater than or equal to 0. So what we want to do in seismic hazard assessment is estimate A and B. But doing that well requires being careful about catalog completeness. So to show you how this works out, I'm going to use some simulated data. So this plot here is all simulated random data. So it's simulated random data. I did 10,000 earthquakes, fake earthquakes, from magnitude 2 to magnitude 7 with a B value of 1. So any deviations from Gutenberg-Richter behavior are due to sampling and small numbers of large events, because this is fake. I know that it really should meet B equals 1. So here we have magnitude on the x-axis. This is a very standard plot. And here on the y-axis, we have log of the number of events. The filled triangles are what we call cumulative counts. So this filled triangle gives me the total number of earthquakes greater than magnitude 2, which I created to be 10,000. This open triangle tells me how many earthquakes are actually round to magnitude 2, and I rounded from 2, 2.1, 2.3. So we see that there's fewer 2.1s than 2s, fewer 2.1s and 2.2. So we plot both the cumulative counts and the filled counts. Of course, remember that this is a log scale here on the vertical axis. So the Gutenberg-Richter relationship tells me that these things should fall on straight lines on this plot until we get variations due to random behavior. Okay, so now I'm going to just compute this equation, get A and B. I'm only going to show you what B is. It's 1. And one lesson here, and you can see that it fits the data very well, and it starts deviating once we get really about fewer than 100 earthquakes. So a couple of things. In the paper I recommended of mine, I have references, not things I created, but the things I choose to use for how to compute Gutenberg-Richter fits. And starting with Kei Aki, who I was very lucky to study with at MIT, starting in a paper he wrote in 1965, we always use maximum likelihood estimates, MLEs, to compute the A and B values. You will see sometimes that people will use least squares analysis to do this. A paper by Karen Bender in 1983 showed that that was a biased method and would give you a bad answer, especially when you have small numbers of earthquakes. The other thing I want to point out here is notice that at very large magnitudes, there seem to be too many earthquakes. And this is a misfit at large magnitudes that's due to a biased sampling because there's a skewed distribution at small numbers. It's skewed high compared to its mean. I will discuss that more in my lecture in about a week on the Poisson distribution. But just be aware of that. It often means that people think we're underestimating the numbers of large earthquakes, but really we're correctly estimating the mean, and this is representative of random sampling. Okay, so now what I want to do is, the last plot showed all the data. I want to simulate incomplete data. And so what I did was I kept all the data with m greater than or equal to 3, and I randomly threw out more and more data as the magnitudes got smaller. And that creates this curving over. That's very characteristic of what we see in earthquake catalogs. As we get below the completeness, it starts curving over. I just did it artificially here. So now I'm going to compute the B-value estimate, the Gutenberg-Richter fits, if I use magnitude greater than 3. So that's the red line. And you can see I get a very good fit. I get a B of 0.99, very close. That's just some random sampling differences because I only have about not quite, I don't have 10,000 earthquakes anymore total. And certainly magnitude 3 and greater, I seem to have about 600 or 700. But if I thought the catalog was complete down to magnitude 2, I would get this line with a B value of 0.55. So this would be a very bad estimate of the rate of large earthquakes. We would be estimating way too many large earthquakes. This is an extreme example, but to be honest, we do see papers where people maybe don't go all the way down here, but they might use a slightly lower value, maybe in between, and they would get a biased, maybe they get a line in between. So we need ways to find a valid magnitude of completeness so that we can then use that as the minimum magnitude when we compute the Gutenberg-Richter relationship. And I'm putting down here a paper. It was also in the abstract I sent out by Arnaud Mignon and Joachim Wosner. It's in the community online resource for statistical seismicity analysis. This is a thing we created as a group and need to update more, but there's very, very good paper on the methods for estimating magnitude of completeness. This paper is how I learned how to do this. I highly recommend it. Okay, so let's look at some of the methods for doing these things. So the first method that I think gets used the most often is maximum curvature, sometimes just called MAX-C. And it was by Stefan Wiemer and Max Wies, and they published it in 2000. And as I said, it's the most commonly used objective method. I say objective method because a lot of people will do this just by eye. So what it looks for is it looks in the bin counts. These are the bin counts here, the open triangles, and it looks for the place of maximum curvature. In practice, they realized that if they just found the value with the most points in it, it almost always was very close to the point of maximum curvature. So this is a very simple method. You just plot up all these bin counts, and you go, oh, look, this one has the most in it. That's the maximum curvature. That is our estimate of the magnitude of completeness. And the dashed lines here, and one of them is hidden underneath this, these are actually show the uncertainty done with a bootstrap. So, and then here is the true completeness, because I know what it is, because I made up the data myself, actually earlier today. So I'm sure I remember that it was magnitude 3. Okay, if I, however, think that it's actually here, which is magnitude 2, 2.1, 2.2, 2.3, I get a B value of 0.79. And so what's happened is I've underestimated magnitude of completeness, I've underestimated B, and I overestimate the number of large earthquakes if I'm doing a hazards assessment. If I use the true value, of course, here's the line that we saw before. So this shows the difference between getting an underestimate and getting the true value. To be honest, it's very well known that MAX-C, oops, let me go back. It is very well known that MAX-C underestimates MC and B, and so people often will increase the MC by about 0.3 units, which would have gotten us from 2.3 to 2.6, and to be honest, would have given a much better answer. So I think it's important when you read a paper and someone says they used maximum curvature, see whether they increased it by a little bit. Hopefully they did. Another method they came up with in the same paper works a little better in my mind. This is one of the better methods, and they called it goodness of fit, GFT. And what it does is it fits the Gutenberg-Richter relationship to the data with a variety of magnitudes of completeness, and it picks the lowest one that has a low residual of the fit between the GR fit and the data. So it says I want a good fit I want data that really looks Gutenberg-Richter, but I want to do that with the smallest possible MC. And here we get a value here that's 2, 2.1, 2, 3, 4, 5, 6, 7, 2.7 plus or minus 0.1. And to be honest, we get a pretty good, with this data, we get a very good estimate of B and of the rate of large earthquakes. So it underestimates B and MC, but only by a very small amount, probably within the uncertainty. Here's another one that I've used, median-based analysis of segment slope. I think he wanted to call it MBAS. Oops, I have an extra S there. And this was by Amaresi, published in 2007. So what he does is he looks at the data and he tries to find a break in slope. And he uses change point analysis. And here it says, well, this data looked like it has a slope here. And here we have a slope there. So this is about 2.4, but notice there's fairly wide uncertainty. The top end of the 95% confidence range gets almost to the true value. But if I use the median value of the bootstraps, I do get an underestimate. I don't actually tend to use this method very much anymore. What I would say is it, in this case, underestimates MC and B, but it has very large uncertainties and it can be unstable. In small data sets, it sometimes will latch on to something like a change up here where the numbers get small, and it will give a gross overestimate of the MC. And finally, I want to mention a method called MC by B value stability, MBS. This is by Cao and Gao in 2002. And what it does is it keeps increasing MC, so it keeps going up by 0.1s until the B value becomes stable and further increases of MC do not change the B value. This makes a great deal of sense because what we want is a stable estimate of the B value. That's what's important when we do probabilistic seismic hazard analysis. And so here we have the median value and we can see the uncertainties in orange. And even though the median value gives a slight underestimate of the true MC, the B value really gives us the same value. There's no difference, and certainly the true value of MC is within the uncertainties. This is a very good method. I will say that it can be unstable for small data sets, but small data sets are always a problem. Okay, so let's look at this in practice, and these are figures taken from my 2014 paper where I was looking at the ISC GEM catalog in their first version. We're going to look at the very recent data. This was the end of this catalog, 2004 to 2009. And I applied all the methods, and we notice here MBAS in red gave a median value of 7.7. Like I said, it sometimes latches onto things up here, and it had very large uncertainties. Most of the other methods gave somewhere between 5.6, 5.7. MBS gave all the way up to 6.1. And I'll be honest, when I looked at all of these different methods, either 5.6, 5.7, MBS said it could be this high. And I also looked at the data. I picked 5.7 as an MC. I still found it useful to be guided by these objective methods, but to make a choice between them subjectively, which was a criticism I received in this paper, actually from Arnaud Mignon. He's a very smart, and but I was able to convince him that I couldn't do better than having to be a little subjective. If we go back in time, now 1955 to 1963, so you'll recognize that this is before the Worldwide Standard Seismographic Network. And all the methods now give values between 6 and 6.5 with their bootstrap uncertainties, well, except for MBS goes to 6.7. And I looked at the data here and I chose a value of 6.5 because you see it keeps increasing here in the bin counts, but 6.5 to 6.4. There's fewer earthquakes in the 6.4 bin. That doesn't seem complete to me. All the bins should always be increasing, especially when we have at least 50 or so data in them. And finally, I'll go back very early. This is 1918 to 1939. Notice these dates are actually sort of bounded by the world wars, and they did both actually impact global seismology. So this is why this time period was picked, was based on knowledge of seismographic network operations around the world, as tabulated and discussed by the people who created the ISC GEM catalog, not me. And here it seems like most of the methods give actually sort of an underestimate between 6.3 and 6.5, and the MBS method shows a little bit higher, but again, there's this step down here, so I chose magnitude 7 as the completeness at this early time period. And what I want to point out is if here in this table, you can see the time periods I looked at, chosen by various changes in seismographic operation around the world, and you can see the MCs, they get smaller and smaller and smaller and smaller. One thing I want to make a point of is it's very important to look at subsets. If you put all of this data together, you would get an estimate that was lower than the true completeness, because you would get an estimate that's lower than magnitude 7, and it wouldn't really be complete back to 1918 or 1900 to magnitude 7. So it's important to divide things up by time. Okay, a few final points. After large earthquakes, there's temporally varying incompleteness. So this is a plot of actually magnitudes here versus time, days, since the magnitude 6.4 Ridgecrest foreshock, and then the 7.1 Ridgecrest main shock. And notice that if you look at the number of the earthquakes, you can see that we don't record small earthquakes for a while after each of these earthquakes. And things improve quickly with time, but it's very hard. The earthquakes are happening so fast, you can't get them all. There's some models of this. Helmsteader et al. In BSA in 2006 and Heinzel and SRL in 2016. We actually use the Helmsteader model when we compute USGS aftershock forecasts for large earthquakes in the US and its territories. And Page et al. BSSA 2016 describes that. The important thing here is you can obviously see if I assumed that I knew all the earthquakes down to magnitude 1, I would think that there were fewer aftershocks and I would change my model. So it's important to take into account this temporally varying incompleteness if you're studying the times right after large earthquakes. Finally, as you've seen, MC is uncertain. And so I think it's always important to try different values to see if your results are robust. So what these plots are here is a comparison of the times between earthquakes, magnitude 7 globally from a declustered catalog. So this is a cumulative number of times between earthquakes. And then the red is the fit to a Poisson model, and it fits very well. And if I check 7.5s, it still fits very well. And actually, even for 8s, it fits very well. And the p-values are very high, so we cannot reject the Poisson model. So again, the main point here is not to understand this paper in a very short time, but just that if I look at data and I'm not sure about completeness, by trying different levels and seeing if my conclusions would change, I can make certain that I'm not making a false conclusion because I misestimated the magnitude of completeness. The last thing is remember that magnitudes are complicated. You know, please go read some papers sometime on how magnitudes are computed. Papers maybe by Gail Atkinson and her students in BSSA. You know, magnitude is a strange thing. When Richter made it up, actually for the local magnitude scale, which is actually the data shown here, but much later, it's the amplitude, corrected amplitude at a number of stations and then averaged. You know, a moment magnitude is much more sense because it includes the, you know, the orientation of the focal mechanism and the directivity of the focal mechanism. But you know, magnitudes they're just really very difficult. They're harder, to be honest, than earthquake locations, which is why I've used magnitudes, but I've only computed earthquake locations in my career. This was a very nice paper by Tessa Torman and colleagues in BSA in 2010. And what they showed was that the Southern California network had changed how ML, which was the Richter's original local magnitude, how it was being computed by the Southern California seismic network changed, and it would actually had a significant change on B value and estimates of large earthquake rates. So at the time they wrote this paper, and I think it's gotten better since then, the old MLs were from 2002 to 2007, and the new ones were 2007, just those 2 years. And those are the ones in red. And you can see that there's a difference in the slope, especially at these small magnitudes. This is a blow-in of magnitude 2 to 3. And this difference in slope would extrapolate out to a significant difference in the rates of large earthquakes. So just always be aware to look at the data, know whether things have changed in network. The catalogs will tell you the types of magnitudes, whether they're moment magnitudes, MWs, surface wave magnitudes, MSs, local magnitudes, MLs, or a number of other types. Very important to remember that magnitudes are complicated and be cautious, which is a good reason, again, for trying different levels of MC and making sure that your results are stable. Okay, so that I'm going to conclude, and then I can answer questions. So first, I just want to say that earthquake catalogs are a phenomenal view into the world. I have behind here, again, the global earthquake map. When I was in college, I got a paper copy of what existed at that time of a global earthquake map. And we would just stare at it and look at it. It's so much information. But remember that catalogs are not data. So they're not certainty. They contain errors and the biases of different types of analysis. Do you care about completeness? Well, for studying locations, not really. For rates, yes, very much so. Always do exploratory plots, such as magnitude time plots. Learn to understand your data. I've at times found changes in networks that even the people currently at the network didn't remember existed. Compute the magnitude of completeness. Use multiple methods for comparison. Be conservative. It's better to be too high than to be too low. And try different values to see if your conclusions are robust. Remember that there are changes and be aware of magnitude types and calculation methods over time. So you can, if something looks weird in your data, look into it in depth. Remember that completeness changes after large earthquakes. So if you're looking really in detail right after large earthquakes, you have to be cautious. And since I do that a lot now, working hard on aftershock forecasting, this is something we spend a lot of time thinking about. Finally, reach out to the seismologists at the networks with questions. It used to be that we had to be in contact with them to get the data. And now it's so easy to get the data, maybe it's easy to forget to ask. But we're still here. And I want to point out that actually perhaps the reason I'm giving a talk in this series is that, quite a number of years ago now, when he was a graduate student, Dr. Brewer reached out to me to ask me questions about some of my papers. And we've become friends at a distance over the years and had many great conversations. And I want to honor him for this, the way he acted and to reach out and to build a friendship and a collegial relationship and to ask questions. Don't do your work in a vacuum. It's not necessary. And I think that's the best way to make sure that your work is very good. And finally, I just want to say as a summary, counting earthquakes may be hard, but it is very important, especially for hazard assessment, so do it carefully. Thank you very much, and now hopefully there are some questions.
Thank you very much, sir, for your nice presentation on earthquake catalog. Now over to Professor J.R. Kyle for his remarks. Kyle, sir.
I think, yeah, excellent lecture, Michael. You have actually opened our eyes, to how to examine the catalog data and how to be careful. I have a query. Can we take magnitude 7 and magnitude 5 as the threshold magnitude for the data 1964 till today? Means since 1964, could it be magnitude 5? Could be the completeness?
That's a good question. I'm going to go back. So I think from 64 onwards, in the Centennial Catalog, or the ISCGM catalog, not there, not in that catalog. It's magnitude 6, but I think in some other catalogs, yes. I think they just didn't process the smaller earthquakes. It's certainly very close to magnitude 5. It might be 5.2 or 5.3, except of course right after very large earthquakes. So after magnitude 7 and 8 earthquakes, there'll be some missing ones there. So close to magnitude 5.
Thank you so much. Thank you.
Yeah.
Yes, some participants who are working
yes,
in.
yes. There are certain questions, and about to Antara Sharma for the question answer session.
Thank you, sir. Good morning, sir.
Morning.
Sir, thank you. First of all, I want to thank you for your beautiful presentation. Sir, there are lots of query in the Q&A section. Sir, may we proceed for the question and answers session?
Yes, I think yes, yes.
Okay. First question is, how we calculate theoretically the threshold magnitude recorded by a network which consists 8 observatories within 100 kilometer?
So I find the best way to do that is to eight observatories within 100 kilometers is a pretty good network. I best is to wait until you've seen the catalog of data, to maybe at least 100 or 200 earthquakes. There are some other methods to look at the number of phases being recorded for each earthquake. There's a paper by Daniel Schloremer that looks at a phase method that might get the answer a little sooner. With 8 stations within 100 kilometers, so most earthquakes will have a station within about 10 kilometers. I would absolutely expect magnitude 3, maybe 2.5. But I'm guessing a little bit there. It also depends on how noisy the area is, in terms of societal noise, and it depends on the analysis methods. Of course, the methods for detecting earthquakes are getting better and better with time, and so that will help us also.
Thank you, sir. So next question is, do we have universal relation converting MW scale into MB and vice versa, or what is better conversion formula to make homogeneous catalog?
I would say not a universal conversion for any of these things. Especially, MB to moment magnitude is very difficult because, so to explain more than I'm sure the person asking this question knows more than I'm going to talk about. So I will do this for other people in the audience. MB is measured at fairly high frequencies, so maybe periods of several seconds. So not super high, but fairly high. And so when the earthquake source becomes larger, you start getting destructive interference between different parts of the earthquake source, and the MB saturates. It stops going up. So maybe after about 5.5, the MB stops going up. No matter whether it's a magnitude 6 earthquake or a 7 earthquake, you get about the same MB. Same thing happens to surface wave magnitudes, which are really measured at 20 seconds. And when the source gets to be maybe 30, 40 kilometers long, you get the same destructive interference. And so I think it depends specifically on each, not all MBs and MSs are computed the same way, so it's impossible to have a universal thing. But I think, in a certain magnitude range, you can make plots of MB versus independently estimated MWs and come up with an empirical relationship for that area. I think it's a problem that we don't have enough relationships for these things. Of course, to get, magnitude MSs will be good to around magnitude 7 or so, and then we really need MWs. Fortunately, as you look at the catalogs over time, so many earthquakes now are just immediately, directly being MWs, and that's a huge step forward.
So thank you. Next question is, sir, what is the best value of magnitude of completeness for any data? Can we toggle it for high coefficient of determination?
Can you repeat that? Is that in the published list of questions?
Yes, yes, sir. The third one. What is the best value of magnitude of completeness for any data?
The best value for any data. So for any data, any earthquake catalogs, what I've been trying lately is I take each of the methods, and actually not using MBAS, but I use the other 3 methods, and I compute the bootstrap, and I take the median. So that helps me make sure the data is not sensitive to a small catalog, and I take the maximum of the 3 methods. So you can't do that. It's not the same for every data. So for instance, I was recently doing this where I'm in the process of updating the seismic hazard map for Hawaii. And from 1959 onwards, in Hawaii, we have magnitude 2.9 and greater, is what we came up with. But we did that by looking at each decade and each area, whether they were the volcanic areas or the non-volcanic areas. And so we looked at many, many different determinations over time and space, and we eventually said, okay, 2.9 is one we can apply to everything. That's very low for 1959. And I think maybe people who are older and will remember Jerry Eden, who was a seismologist at the USGS, and 1959 is when he went to Hawaii and built the seismic network there. He was a extremely detailed, careful observational seismologist, and I was very lucky to study with him for my postdoc. So I was very happy to see how good his catalog was. But you couldn't do the same thing in California. We would not be at 2.9 in 1959, and globally, of course, never. So there's not one thing you can do.
So next question is, do you think sharing data from local seismic network from individual country can improve the result of global earthquake completeness?
Yeah, to a large degree it can. And I think we see that, for instance, in ComCat, which takes global data from some sources and also many regional sources within the US, like the Northern California and Southern California networks, the Puerto Rico seismic network. And we can make a catalog that's better than just our national network. And the same thing can be done in the global networks to a certain degree. It works on where we have land and where we have seismometers. So it can't work for the oceanic areas because so many of them there just aren't seismometers. 2/3 of the world is very difficult to run a seismic network. So yes, sharing data is critical, and I think in the ISC GEM catalog you see that they are doing different processing for where there is landmass and where there is ocean. Very important for us to share data. I think that's something that's really grown in seismology over the years. It's always been a tradition, but we've gotten better and better at it. Very important.
So next one is when analyzing foreshocks, aftershocks, or earthquake swarms, we often try to plot B-value variation with time. How many events at least statistically suitable for a time window to get reasonable estimates of B-value?
Really good question. Yes, so there are people looking at B-value variations in aftershock sequences. Many people may be aware of a paper by Laura Guglia and Stefan Wiemer in Nature about a year ago, saying that in an aftershock sequence, when you see the B-value drop after the main shock, that this may be a foreshock. And this is a very tantalizing idea. When we look at their plots, we see even with using 200 earthquakes at a time, that there's a lot of variation, more variation than I think should exist. I think it's very difficult. I think it's very difficult in aftershock sequences because not only do you have increased incompleteness after the main shock, but after each large aftershock. So it's very difficult to make sure we're not mapping this temporal variations in our ability to record earthquakes with these variations in B-value. I would always do robustness checks. I would keep increasing the size of the windows until you get a stable result, until it's no longer changing. I think their windows are a little short. I will also say that I'm very hopeful that one of my colleagues is about to submit a paper with some new methods for doing this that will make things more stable, but I can't talk about what he hasn't submitted yet. So a very difficult problem, very important problem. I would just say keep trying different bigger and bigger numbers and see when it gets stable.
So next one is what are the challenges in creating a combined catalog from various networks for a region, like using local network, ISC, GEM, and USGS, altogether for a homogeneous catalog?
All right, there's two basic problems. One is you put together the catalogs and you have to get rid of the duplicate earthquakes. especially the global catalogs. If you take the USGS NEIC catalog and the ISC catalog, there's going to be a lot of duplicates. So you have to go through and then decide which solution you want to keep. The other, what we do in the US is each of our regional seismic networks has an area of which it has authority. And so if an earthquake is in Southern California, we use the Southern California solution. If it's Northern California, we use Northern California, unless the Northern California solution is missing. And then in the gaps, we fill in with the national catalog. So first you have to make sure you have only one copy of each earthquake. And then it's a question of which location and which magnitude you think is best. So for instance, we also will do things like in Alaska, we will use the Alaska location now, but we might, for larger earthquakes, use the national network's magnitude. So it's a question of knowing the strengths and weaknesses of each network in each magnitude range and trying to put it together. To be honest, I think the best calculations are done when, instead of putting together just the earthquakes, you take all the phase data, all the data for each seismogram, and you put those together and merge those and try to do a new calculation of location and magnitude based on the raw data. Well, at least the arrival times, the phase data. Even better would be to put all the seismograms together. So I think it can be done on various scales.
Sir, can we proceed for more questions? There are actually lots of questions in the query box.
Sure, I can go for a while longer, yes.
Okay. So next question is, how the rate of movement of small and large plates vary?
That question I'm going to suggest will be better answered by some of our later speakers who are actually talking about tectonics. Generally, the plate motions don't seem to vary very much over scales of decades and even sometimes millions of years. But the rates of earthquakes may vary more frequently than that. But I think better some of the other speakers will address that.
The next one is, you mentioned about the fault orientation with limited earthquakes. Is it always accurate? There may be other weakening zones, but not the main fault itself.
Well, hopefully in many earthquake sequences, we image many faults. And but yes, there could be a big fault nearby that's still locked that we don't see. I mean, if we look at a map of, say, California, the San Andreas fault in Northern California does not reveal itself with small earthquakes. It's almost aseismic. The same is true of the interface of the subduction zone in Cascadia, Pacific Northwest, in Oregon, Washington, and into Canada. So yes, earthquakes can tell us a lot, but only about the faults that are actually producing earthquakes. And there can be very important faults that we will not see.
Okay, sir. So next one is, the small catalog may be problematic to calculate the magnitude of completeness value. How to take care of this? Is there any condition for making the catalog to calculate the MC value?
Yes, I mean, small data is always a problem, right? This is almost impossible to overcome. I would say, looking at the network, as someone asked earlier, if you have 8 stations in 100 kilometers and you look at other places in the world with similar numbers of stations, but maybe more earthquakes, you could see what magnitude of completeness they achieve, assuming you're doing a similar job of analysis. And then you would be able to answer the question, for instance, is the small number of earthquakes here because there really aren't very many earthquakes, or because we're not doing a good job, we don't have enough stations to record them all? So maybe I would use some comparisons to other places. Yeah, I mean, there are places where there are important faults that are locked and aren't producing many, small earthquakes. This is also where, for probabilistic seismic hazard analysis, geologic studies are very important. So for instance, I mentioned the northern San Andreas produces very few earthquakes. If we tried to calculate the hazard of the northern San Andreas, which produced the 1906 earthquake that destroyed San Francisco, we would not be able to compute the rate of that earthquake from small earthquakes, because the fault just doesn't produce any. It's locked, completely locked and silent right now. But we can dig trenches and do paleoseismology, and then get a rate of earthquakes, of large earthquakes, from geology. And so comparing these things can help us at times when maybe seismology isn't the only answer.
I think one more question you take up,
Okay.
because he's getting tired now.
Yes.
Maybe one. This is last question you take up, or you
Okay.
you choose the which is more complicated question, and you can ask that question.
Yes, sir. You can choose from the published section.
All right. So I'm going to answer two of them actually. So one is on bootstrapping. Okay. I think bootstrapping is very important because I like bootstrapping very much. What bootstrapping does is it gets you to not have to guess about the errors in the magnitudes, and the uncertainties in magnitudes are very difficult. So bootstrapping, computers are fast now. We can do bootstrapping, and I was very lucky to be introduced to bootstrapping when I was at Stanford in the 1980s when it was being invented there. So maybe I'm a bigger fan than most because of that. But I think any time you can apply bootstrapping to a problem, it's worth a try. The other one, should we trust p-values for seismic hazard analysis? How do we account for the variability of natural randomness? Well, we only use the p-value to give us the average rate. And then the randomness, the variability of natural randomness, we get from applying a Poisson distribution in probabilistic seismic hazard analysis. This is fundamentally what Alan Cornell did in his seminal 1968 paper on PSHA. The other part of the question is, do we trust the p-values to be stable over time? And that's a good question. Most places, when we look over long periods of time, over decades, not over the short variations during an aftershock sequence, they do seem quite stable. But we should always, when we do probabilistic seismic hazard analysis, is use a logic tree to account for the uncertainty in the b-value. So do a b-value, three things: b-value, b-value minus 1 sigma, b-value plus 1 sigma. So always good to account for variability, both with the Poisson distribution and using a logic tree to account for uncertainty. And I think, yes, there, maybe I'll stop. I'm sorry, I can't get to more questions. If people want to email me, maybe that was in my abstract, I am always willing to correspond. If I get a lot of emails right away, it might be a little slow. Thank you so much.
Send those, yes, thank you very much, sir. So we'll send the questions to you, get your answer. And thank you once again for accepting our request for delivering this talk. Now over to Mr. Prasijya Patakur for the vote of thanks. Over to Prasijya.
Thank you, Dr. Santanu sir. I, on behalf of CSIR NIST and the entire organizing committee, we were very thankful to Professor Andrew Michael for sparing his time and giving us such an informative talk and give a deep insight about the Completeness Catalog. We are very thankful to you and storing upon us your great knowledge and the experiences that you gather over the years. And I hope the participants today learned a lot from your talk. And we have another talk from you on Poisson's assumption on 22nd September at 9:30 IST. We are also looking forward for that talk also. Once again, I am very grateful to you, sir, on behalf of our organizing committee for sparing your valuable time from your busy life and spreading knowledge, showering knowledge upon us. Thank you, sir.
Thank you so much. Yeah.
You're very welcome. I very much enjoyed doing it.
We all enjoyed, Michael. Thank you so much. Thank you so much.
And nevertheless, we thank our respected director, sir, Professor J.N. Sastriji, for giving his permission to conduct this international workshop on global seismology and tectonics. And we are very grateful to Professor J. Narahal Shastriji for his tremendous support and guidance in each and every step in the successful conduction of this workshop. And not to mention our chairperson of this session, Professor J.R. Kyle, sir, and the co-chairperson, Dr. Saurabh Barua, sir, for their continuous support and guidance in each and every step of this international workshop. The problems that we face in every step, you too, sir, with us in every step, and helping from your tremendous experiences, and a successful conduction of this workshop happens only because of you, sir. And thank you once again for sparing valuable time from your busy schedule. And not to mention our convener, Dr. Santanu Bolwa, sir. We, on behalf of all the participants, thank you, sir, for giving us the great opportunity to interact with such a prominent figure in the field of international seismology. And we are so grateful to you, sir. And not to mention the active participation from all the participants across the world for their great participation. And we saw in the question answer section, there is a lot of queries from the participants end, and that means we have a successful completion of this talk. And I hope their queries are solved by our delighted guest, Professor Andrew Michael. I'm sure that it was a great learning experience for the participants too. They learned a lot today from hearing from such a prominent figure. And once again, we thank you, Professor Andrew Michael, sir, for his such an informative talk, and love from India. Thank you, sir.
Thank you so much. Thank you.
Thank you, sir. Good night, sir.
Thank you. Okay, so I